Okay. So yesterday we had been talking about, we talked about graphing parametric functions. We talked about going from parametric to Cartesian. And then we started talking about Cartesian back to parametric. I want to do a little bit more on this today before we move on to our next topic. Okay, so those are the three things that we looked at yesterday or last time. Was it yesterday? No. Okay, well, last time. So a couple more examples of, again, going from Cartesian to parametric form. Okay. So this first example, we're going to be asked to find the parameterization of the line that passes through the points 3, 9 and negative 5, 2. What's one way we could do this? Anybody with an idea? Well, one way we could do this, maybe the first initial obvious way, is to write the slope-intercept equation, right? We have 2 points. We can write the y equals mx plus b equation pretty easily. Everybody kind of remember how to do that from your Algebra 1 course? And then we can just convert this to our parametric form by just saying x is equal to t and y is equal to mt plus b, right? Which would be rather easy. And the one last thing we would need then is the interval for this, or for our parameter. What are we trying to describe right now? What kind of graph? Reread the question. What are we trying to describe right now? What shape is this graph? A line. A line extends in both directions forever, right? So what do you think my interval is going to be? Yeah, negative infinity to positive infinity, right? And as long as we're talking about a line, this is a perfectly reasonable way of approaching this. If this is a segment, though, this approach becomes a little bit more problematic. What I want to do in that case is talk about an alternate way that we could approach this kind of a problem. And that's using the vector equation for a line. So if you remember, the vector equation for a line is r equals r naught plus vt. What did R naught represent? What kind of vector was R naught? Nope, that's VT, or V was the slope vector, direction vector. R naught was just a point vector, right? So in our case, R naught could just be either one of the 2 points, either 3, 9 or negative 5, 2. Everybody's okay with that? Doesn't matter which one you choose. And vector V would either be the vector AB or the vector BA, right? So let's say we find the vector BA. So that's going to be 3 minus a negative 5, and then 9 minus 2. So that's going to be the vector 8, 7. So my vector equation, if I use point A and vector BA, I have this equation. Everybody kind of remember doing that from just a chapter 2 ago? So right now, this immediately gives me my parametric equation. So I can say x is equal to 3 plus 8t. That's how I find the x coordinate. And y is equal to 9 plus 7t. That's how I find the y coordinate. And since it's a line, the parameter, or the interval for the parameter, is just going to be all real numbers. Is everybody okay with that idea? So let's do another example, and this time find a segment rather than a line. And I can really illustrate to you the advantage of using that vector line equation. Just as an aside, when I say find a parameterization, what do I really want here? So a parameterization is just asking for the parametric function. So we're going to approach this the same way. We're going to start by writing a vector line equation. So for R naught, I'm just going to use the point negative 1, 4. And then I'm going to use the vector CD. So that's going to be 6 minus a negative 1, and then negative 3 minus 4. So there's my vector line equation. So that immediately gives me these two parametric equations. The last thing I need is my interval for t. Okay. Let me point out to you that this point is one of the endpoints for my line segment, right? So what value of t do we know needs to be included in this interval? Let me ask this question again. Negative 1, 4 is one of my points, one of my endpoints for my line segment. So if you look at our vector line equation, what value of t must be included here? What value of t is going to give you the point -1, 4? 0, right? Can everybody see that?
Yeah.
So I know that t equals 0 is going to give me the point 1, 4. Well, all I need to do now is check then to see if which way this vector line equation is really pointing, if it's pointing to the right or to the left. So either t equals 1 or t equals -1 is going to give me my other point. I just need to check to see which one it's going to be. So if I do that, I get -1, 4 plus 7, -7, which gives me 6, -3. That's what I needed, right? Because that was my other point. Do we see that? So what's my interval going to be then? Zero, 1. Okay, so I didn't even have to bother trying t equals -1 because I got the other point immediately with t equals 1. Okay, so that's kind of the advantage there of not using the Cartesian form to create our parametric equation, but rather using that vector line equation, is that we're always going to have a unit interval for our parameter, which is nice. So section 10.2 is going to be about an application of parametric functions, specifically like two-dimensional motion. How many of us are in a physics class or have taken a physics class? Okay, so like a handful of us. Those of you that have or are currently in that situation, what we're about to do should look rather familiar. So I'm going to start by just giving a few equations here. So the height in feet and the vertical velocity in feet per second of an object in free fall, ignoring friction, after t seconds is given by the equations. So what do the letters in these equations represent? G is for gravity. T is for time in seconds. V naught is the initial velocity of the object. S naught is the initial height of the object. Does anybody remember what gravity is? So negative 9.8, but what's the unit? Meters per second squared. What unit were we working on in this, though? Feet. Does anybody remember gravity in feet? It's negative 32 feet per second squared. So this really just becomes negative 16. And this one becomes negative 32. Why is gravity negative? Because it pulls things down. Yes, very good. Okay. So let's look at an example here. All right, a ship is stranded in the ocean. On top of the bridge that's 80 feet above the water, a distress flare is shot straight up with an initial velocity of 72 feet per second. Provide the graph of the flare's height above the water against time and find the height of the flare at t equals 1, 2, 4, and 6. So what are we looking for in this problem? The height of the flare. So which of the two equations am I going to use? S of t or v of t? S of t. Okay. So what are we plugging in for v of t? What are we plugging in for v of t? 100% is not correct. 72. And what are we plugging in for S sub 0 or S naught? 80. Okay. So let's go ahead and graph this. So I'm going to change my mode back to function mode. Okay, so here's my graph. Everybody's okay with this? So the x-axis is representing t, or time, in seconds. The y-axis is representing s of t, which is the height of the flare at that given time. So the easiest way to find these value, or find the value of S1, S of 2, S of 4, S of 5, is to just press second and the trace button and use the value command. So it's going to ask me to input a value for x. So for example, I can put in 1 and it tells me when t is 1, y is 136. And if I want t equals 2, I get 160. And when t equals 4, I get 112. And when t equals 5, I get 40. And I guess these are feet really above the ocean. Is everybody okay with this idea? Notice that I didn't really have to use a parametric function at any point here, right? Why did I not have to do that? Because really what's happening is that since the flare is being shot straight up and down, the x distance the flare is moving is 0, right? It's not moving anywhere forward or backwards, it's just going straight up and straight down. And really, I guess we could just say, could think about this as the discrete set. Now, using a parametric function to describe something that's moving only one-dimensionally, like something that's being shot straight up and down, not very interesting. Or a bit of overkill anyways. Our Cartesian form describes this quite nicely all on its own. Where the parametric function is going to be much more practically useful for us is going to be if I'm firing or lobbing something at an angle. So if you're throwing a baseball, that baseball is going both forward and up and down, right? It's moving in 2 dimensions rather than just one, as if you threw it straight up and caught it. It's in that situation in which the parametric equation is going to become really helpful for us. So let's define a few more equations. Okay. So an object in projectile motion with an angle theta taken from the horizontal, an initial velocity v in feet per second, can be represented by the vector v equals the component form magnitude of v times cosine theta, comma, magnitude of v times sine theta. The distance x and the height y in feet can be given by x equals the magnitude of v times cosine theta times t, and y equals negative 16t squared plus the magnitude of v times sine theta times t plus s naught. And the horizontal velocity v sub x and the vertical velocity v sub y, both in feet per second, can be given by the equations vx is equal to the magnitude of v times cosine theta, and vy equals negative 32t plus the magnitude of v times sine theta. So let's use these new equations that we've just been given to do a maybe more complicated problem. All right. For all my baseball players out there, you hit a baseball at 3 feet above the ground with an initial speed of 135 feet per second at an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence that is 300 feet away? If yes, by how much? If no, how high up the wall will the ball hit? So, which one of these two parametric functions are we going to be interested in? The xy or the vx vy one? The xy one, because we're interested in heights and distances, right? Okay. Okay. So let's start filling in some values here. What is my value for the magnitude of v? What is v representing? It's a velocity. So what number should go in for magnitude of v? Very good, 135. And then we'll have cosine of theta. What number is theta? 16. And then we still have our variable t. And then y. And what is S naught in this case? What is S naught? Not 15. It's the initial height. So 3. Okay. So, what am I going to do here? So this is going to, that parametric equation or function that we just written is going to describe how the baseball moves. Everybody's good with that? We want to find out if it's going to clear this fence 15, or this 15-foot tall fence 300 feet away. So what I'm going to do is I'm going to figure out how much time is it going to take the ball to go 300 feet. And then I'm going to plug that value of t into the y equation and see how high off the ground the ball is going to be at that time. Sound good? Okay. So 300 equals 135 cosine 16 times t. So I'll get t equals 300 divided by 135 cosine 16. Then to solve for y, or to find my height then at that time, I'm just going to go ahead and plug that in. And when I type that all into my calculator, I get about 3.51 feet. So what do I conclude? Did the ball make it over the fence? How high was the fence? 15. So this was less than 15. So the ball doesn't clear the fence. Does it hit the fence? Yes. Where will it hit the fence? Just 3.51 feet above the ground. Everybody okay with that idea? Let's visually confirm what we're seeing here. So I'm going to graph this using a parametric function. So I have 135 cosine 16 t. Then I have negative 16 t squared plus 135 sine 16 t plus 3. I'm going to reset my window. My time t, I am going to use what? Okay, maybe that's not totally obvious. Let's go to x mins and x maxes. What's my x min going to be? Well, how about 0? What would be a value for my x max? It's got to be at least 300, right? So I'm going to just round up to 400. How about my y min and y max? Yep, 0, and then, well, I'm going to do bigger than 15. So I'm going to do 50 just for grins. Okay? And I'm going to do one other thing here. Actually, I'm going to graph a second, well, I'm going to graph a second set of equations here also, as long as I'm at it. What I'm going to graph right now, this second set of equations, I want to graph the fence. I can graph the fence. That's not a problem. So what is the x-coordinate of where the fence lies? It's 300, right? Because the fence is 300 feet away. And what's the height of the fence going to be? 15. So the way to get this to put a line that's just like 15 units tall, a straight vertical line, is I'm going to do 15 divided by a variable called T max. So what I'm going to do to get that is I'm going to go to the vars menu. And I'm going to go to the window tab. And I'm going to scroll down till, oops, not scroll down, scroll over and pick T max. And then times T. So that'll fill in all the points from 0 to whatever that last value of T is that we're looking at. So the last thing I need to do now is go back here and decide a value for my T max. Anybody played baseball before? If you hit a long fly ball, how long is the fly ball in the air for? Just give me a guess. Some number of seconds. 7 seconds. Let's round that up to 10. Just to be safe. So there's my fence. And why didn't I get the curve for my baseball? What mode is my calculator in? Probably radians. What should it be in? Degrees. There we go. So there's the trajectory of the ball. There's my fence. And you can see visually here that that ball's not clearing the fence, right? So that's a nice little visual check on a problem like this. Okay with that? All right. Let's do another. Yes. Sure. Okay. So similar kind of question, right? Let's check this on our calculator first, since we have that all set up. On our calculator, we just have to change some values here. So 135, I'm going to change to 141. 16, I'm going to change to 24. And then 135, I'm changing to 141. 16, I'm changing to 24. And then 3, I'm changing to 3.5. And, oops, I guess I forgot to write how far away the fence is, right? Let's say that fence is 400 feet away. So change 300 to 400, and the fence is 20 feet tall, so I'll change my 15 to 20. And then I'll just hit graph. Whoa! What did I forget to do? Yeah, my window's all goofy, huh? Do that. So there's my baseball path, and there's my fence. What does it look like? Looks like it made it over, right? So let's find out how much it cleared the fence by. We'll do that part algebraically. So just like before, I'm going to solve for t using my x equation. And then I'm going to plug that into my y equation. So that's greater than 20. So it looks like the ball clears that fence by a little more than 7 feet. Everybody okay there? All right. What if we assume there's no obstructions and we ask how long will the ball be in the air? Or I'm sorry, how far will the ball travel? Excuse me, that's not what I want. So what am I going to do this time if I want to solve for how far the ball travels? What I'm going to do is I'm going to use my y equation to solve for t and plug that value of t back into the x equation to get the linear distance. Well, at what height would the ball be when it's done traveling? 0. Okay? So how am I going to solve this equation? I'd have to solve a quadratic. Am I going to be able to factor this? Not with a sign of 24 in there as a coefficient, right? So what should I use? Come on, guys. The quadratic formula. Okay. Okay, so when I do that and I solve that quadratic, these are the two solutions I get. Do both these solutions make sense? Angela? Sure. No, why not? Can't have negative time, right? So that one for sure is done. This is what we want. So we'll just plug that in then for x. Excuse me. And when I do that, I get 469.4336006 feet. All right? Yes, Ben. Sure. One more question. Okay? Same situation. Assuming that we have no other obstructions, how far away could we place a 20-foot fence and still have that baseball clear it? So, same idea as the previous problem, right? But what is the value for y that we want to solve here? 20. So, we'll start by getting this equal to 0. And how are we going to solve this? You just said this a minute ago. The quadratic formula. Okay. So when I type that into my calculator, I get two answers. Which of them is the answer that I care about? They're both feasible. They're both positive. We care about the second one. Why do we get two answers for this? Well, there's two places where the ball's 20 feet above the ground, right? Once in the very beginning as it's going on its way up, and then once at the very end when it's on its way back down, right? The one we care about is the one when it's on the way back down, the one way later. So when we do that, we get 421.05 or 0.657,968 feet. So you can place that fence, about 421 feet away. So for next time, 29 to 48.